This is our water temperature control project from Chad, Paige, and Rebecca. Our goal of the project was to control the temperature of the water by adjusting the valve position and thus the amount of heat transfer. You can see we have a pot of water with a heat source underneath in the block diagram. In this system, we define the following variables: the process variable as the water temperature, the set point as the desired water temperature, and the control variable is the valve position. This can be seen in the block diagram as we stated. Pictured is our experimental setup. This type of controller could be used in systems such as a hot tub, cooking, or in the vaporizing of petroleum, colloquially known as boiling oil. This system is defined as follows. This is the energy equation for our system. It includes the convective heat transfer of the flame to the pot, the radiative heat transfer from the flame to the system, the convective heat transfer from the system to the surroundings, and the radiative heat transfer to the surroundings. Our procedure and our plan was first to figure out the thermocouple coating, do step tests and FOPDT optimization, take those to PID IMC tuning initial guesses, and then do more testing such as doublet testing. This project really helped us learn how thermocouples work, and we were able to have real-life experience with a Type K thermocouple. Our initial goal, we were going to have a thermocouple record the temperature and then have a PID controller output a valve position to a servo motor, which would then adjust our valve. However, this proved extremely difficult, and we made Paige be the servo motor. This is the thermocouple we use. It's capable of reading temperatures of up to 2,300 degrees Fahrenheit, which made us comfortable using it with the boiling water. We connected this thermocouple to the Arduino and used this to read the temperature of the water. This was our first step test. We did FOPDT optimization, and these were the initial parameters we got from our step test. From these parameters, we were able to get initial guesses for our PID controller through IMC tuning as shown here. We did this for simple, conservative, moderate, and aggressive. And due to the low responsivity of the system, having a more aggressive model is not necessarily the right answer, as the heat transfer rate is the limit to the system, and the valve, and thus the heat rate, can only be so high. So even if the system is more aggressive, it can't go any faster. We then did doublet tests to optimize the FOPDT some more. We had some, as you can see, that it was kind of difficult to get it to match. And we kind of decided that it was impossible to control the temperature with only a heating mechanism, and a cooling mechanism is also required if a faster response time is desired for cooling. And so without having a cooling system, it was difficult to model the system with the different valve positions and how slow it cooled compared to how fast it heated up. We faced a lot of issues in this project, first with the communication between the servo motor and Python, which we fixed by having Paige be the servo motor. We finally found some example code that helped us have the thermocouple give us temperature. We also had issues with Mac versus PC, as a thermocouple would only work with a PC. We were able to get the servo motor to rotate, but the command between the servo motor, the thermocouple, and Python was difficult. Our initial apparatus also included a propane camp stove instead of a stovetop. However, there was issue with how big the flame was. It didn't get small enough. And through all of these, through this project, we learned a lot about how to use an Arduino, thermocouples, and the difficulties of designing a model of a system.